טוב לכם, תודה שהזמנתם אותי לנהל בסמינר ולהזמין את עצמי להציג בסמינר. מה שאני הולך להציג לכם היום בעבודה משותפת עם אחי האקדמי דודו. ובעצם מה שאנחנו רוצים לדבר עליו זה על second opinion ועל כל מיני אפקטים שמתקבלים כשאנחנו רוצים לקבל שתי דעות משני מומחים. אז ככה, בגדול הסיפור, המודל שאנחנו רוצים, אגב אילן, אם אתה לא שומע או משהו, תכתוב לי את העיר. המודל שאנחנו רוצים לחקור, לדבר עליו, זה מודל של קבלת דעה שנייה, של second opinion, כשיש למומחים שנותנים את הדעה השנייה שיקולים אסטרטגיים. מה שהיה לנו בראש, מה שקופץ תמיד לראש של הדעה השנייה זה בעצם רופאים, הרופא הראשון, ואז אני הולך לרופא השני לקבל חוות דעת נוספת, אבל זה יכול להתאים לכל מיני סוגים של אינטראקציה חברתית, למשל עוד מעט מתחיל המונדיאל, ואז יש את השופט הראשון שקובע משהו, ויש שופט בווידאו שנותן לפעמים חוות דעת נוספת, והעבר, ובכלל באופן כללי בקבלת החלטות מבנים היררכיים בצבא, בעסקים יש מישהו ג'וניור שנותן דעה, והדעה הזאת עולה הלאה, ואז מישהו יותר בכיר נותן את הדעה שלו, ואנחנו מקבלים איזושהי אינטראקציה בין המומחים. ממש על קצה המזלג, בקצרה מה שיש לנו במודל, יהיו לנו שני מומחים שנותנים את הדעה שלהם. כל מומחה כמובן רוצה להיות צודק. בהינתן שהמומחה טועה, הוא היה מעדיף שגם המומחה השני יטעה, כדי איכשהו להתחלק באחריות, קראתי פה liability, אבל באופן כללי כדי תירוץ טוב, אם אני טעיתי, תמות זה היה די קשה לפתור, אז ברור שאף אחד פה לא יודע מה קורה. ג'ונתן נימס. ג'ונתן אנגלית. טוב, כן. So the general idea is that if I'm incorrect, I want the other expert to be incorrect as well, share the liability. It's a hard problem. Of course, I didn't solve it, but the other guy didn't. So you can't really blame me. And vice versa. If I'm correct, I also prefer the other one to be incorrect because if the other one is incorrect, I'm kind of establishing the superiority over him, or maybe if it's a job or something like that, I'll get a promotion because I'm correct and he's not. So in general, I would rather the other expert to be incorrect. And this is a small comment about it, that I want him to be incorrect, but I do want the information that he possesses. So if he's incorrect and he tells something wrong, I can in general, in terms of pairs, I do want the other one to be incorrect. It boosts my pair. And this kind of strategic interaction, this is what dictates the recommendation the expert gives. And what we show that this recommendation might not be in the best interest of the patient that seeks to learn the state of the world or seeks to get the correct opinion. If we zoom in, what we're going to discuss, we're going to model this game of second opinion or situation of second opinion as a two-stage sequential two-player Bayesian game. And what we do in the paper and what we'll do today in the talk, we're going to solve it. We're going to discuss the possible equilibria in this game and map the expertise levels of the experts to the equilibria and kind of vice versa, or equilibria to the expertise level, and then we can predict what kind of recommendation will be given in the equilibrium, the quality of the recommendation, and how we can improve. In particular, we identify two interesting effects in this game. The first one is what we call the humility threshold. And the general idea here is that you don't want to go to a second expert which is too good. And the idea, the intuition is that if the expert is too good, he does not care about the first expert. So he gives his own opinion about his own information, and it might be worse than somehow that is less good, but actually listens to the first expert, and if he listens to the first expert, he has more information to decide. So this is the one interesting effect that we observe in this model. And the other effect is the intern effect, which
this is the result, the rational result that the expert doesn't take into account.
Yes. If you're a too good expert, you might disregard completely the recommendation of the first expert because it's substantially inferior to you, and you do whatever your information tells you to do.
Why totally no? Why not to take it maybe weekly? Okay.
You'll see the model, though. And a second effect which we report is what is called the intern effect, and this discusses the order of the experts. So in general, when we think about the second opinion, typically the second should be better than the first. So this the idea that comes in mind when going to doctors. And what we show that this is not always the best for the patient. Sometimes it is, and from pretty much the same intuition, sometimes it is better to go first to the more experienced, to the better expert, and then to the less informed one, because the less informed or the intern will listen to the first one, and this does not happen when we go to the experts in the reverse order. So you want to go to the intern second and not first.
It is costless.
Yes, I'll show the model in 2 slides, but in general it's costless, and you have to you go to the first, and you go to the second, and you do the entire process from start to over. You don't get to decide whether you want a second opinion or not. And what we also show, and this is from a mechanism design perspective, in some sense, we show that if we change the liability of the experts, we can decide which of the equilibria will be played, and then we can choose the optimal, or actually a set of optimal liability levels for which the experts get to the correct decision with the highest probability, which is in general what the patient, the decision maker, wants. So in terms of existing literature, and what we're doing is kind of on a junction between 2 fields. We're in the junction of social learning with externalities, and we're doing a Bayesian game, a sequential Bayesian game, and we tried, but we didn't find anything that kind of suits exactly our model or our work. It differs from both. So in some sense, this is the social learning because we have 2 experts, and they get to decide and get to try to interpret the state of the world one after the other. But when you think about social learning, the typical questions are about the asymptotic learning. You have a lot of agents, and they learn, and then what happens when you go to infinity. And here we have only 2 agents, and we have only 2 stages, so it's not really connected to the correct or the mainstream literature on social learning. And on the other hand, Bayesian games are typically the ones that the mainstream Bayesian games are more one-shot games and maybe with a continuum of action. And here we have only a finite number of actions, and this is sequential. So we couldn't really place ourselves anywhere in the literature, and this is why the slide looks a little bit weird or incomplete. And by the way, if you have suggestions or anything, we're really eager to hear. We were just insightfully test rejected from one journal, which means that we were test rejected, but they gave us comments, which is nice of the editor. So as we prepare the submission to the next journal, any comment will be taken into consideration. Okay. So let's go to the model and see what we actually have. So we have a decision maker. This is what I used to refer as the patient, and he wants to learn the state of the world. We assume the state of the world is a binary variable theta, which can be either 0 or 1. And the state 0 is more likely, so P is the probability of the state 0, and we assume that P is larger than half. And the decision maker wants to learn the state of the world, so he goes to experts and he consults them sequentially. Each of the experts obtains a private signal with some probability. The private signal will be denoted by S, and the probability that the signal is correct is Q. Of course, we assume the private signals are informative, which means that Q must be larger than P for both agents. And so the first expert learns his private signal and gives his recommendation, which is A1. And generally what everyone are trying to do is to match the state of the world. So his recommendation is either 0 or 1, or basically his best guess the state of the world.
Okay. The accuracy does not depend on the true state.
No, we assume the accuracy is independent. The probability that your signal is the correct state is Q regardless of the true state.
They want to match the action with the state of the world.
Yes. So expert 1 gives his recommendation, A1, and of course wants A1 to be the correct prediction of the state of the world. He wants to match theta. And we assume that this action is, his recommendation is public. So when the decision maker goes to the second expert observes the A1, he observes the recommendation of the first expert, but also he has his own signal S2. And based on all this information, he gives the second opinion, which is A2. And again, A2, he wants it to match theta. Then the decision maker adopts second opinion, and the theta is revealed, and payoffs are given to everyone. Now, before we go to the payoffs, I just want to explain this delicate point. So, why the decision maker adopts the second opinion? And maybe the decision maker is not the best name. We assume the decision maker is not an expert, so he has no information of his own. And he has no way to really assess the recommendations of the others. So what he just gets A1, he gets A2. He has no way to decide which recommendation is better for him. And in general, he assumes the second expert, which is, well, intuitively better, but also seems better because he has more information. So he assumes that expert 2 does all the work for him and gives him the best possible recommendation. A2.
So theoretically, you would prefer expert 2 not to learn what expert 1 did and to conclude by himself to get all the information, clean it from strange motivations and things like that, and then what each one of the experts learned.
Okay.
Why not?
Theoretically, the best.
This is the full information.
Yeah.
Because it aggregates information.
No. Both systems.
Yeah. The best.
Each one of the experts will give him without learning about each other, and then you get all the information.
The best
The
thing
problem
is
starts
to remove
before.
him. The best is to remove him, put here the best possible expert, let him observe both signals and do his magic and give the best information is the best expert you can find, see both signals as they are without
The problem is that they have motivations about the other one.
Yes.
So
But it doesn't.
potentially, I mean, you could receive the information. That's all.
The information is only an recommendation anyway, not a secret itself, right?
But
The same.
expert 1
It's well known the accuracy level. You say what you
No,
got.
it's not the same. You tell him, I have a very strong signal, and I know that your signal is better than the other ones. If you only give a recommendation, then I might think.
No, the signal is only, it's binary. 0, 1.
signals are binary and
So.
and with the cues are well known to the experts. But possibly not to the decision.
Your example of organization is right, the junior one and senior. That's
So in general, the senior would prefer to have all the information the junior has, all the information he has, and assuming the senior is actually a better expert.
And even if not, he's senior, so he has to.
And then you do this mash of all the information. The problem that maybe the first expert masks his information or doesn't report to the S1.
So it's a matter of equilibrium select, because then always equilibrium where N1 is S1.
Yes, but we will see the payoffs in the next slide, and then we'll see that expert 2 has some incentives, not always give the best.
So the payoffs incorporate more than the desire to match the 7.
Yes, yes, exactly. So I just wanted to finish the discussion at this point. So A, we assume that the decision maker adopts the second opinion because he is not an expert and he doesn't know how to do the work of the experts and how to, let's say, resolve conflicts. Of course, if both experts are telling the same thing, it's kind of obvious that if one says 1 and the other says 0, then we assume that the decision maker has no good way to decide which is the true state, so we just go to the second. And the more important to this point, this assumption plays no role because the game that the experts play is a game between themselves of what I recommended, what you recommended, and what is the true state of the world then. Whatever the patient does with this information, I don't care. I just want to be correct. I don't care if the decision maker listens to me or not. I can't force it. So even if we change this assumption to something else about the decision maker, it doesn't change the results or the equilibrium. Okay, what about the things? So we assume that the strategic, that the experts are strategic, and basically there are 4 possibilities in this game. The best one for each expert is to be correct alone, meaning he is correct. The other one is incorrect. This is what we know by U1. Second best is to be correct with the other ones. Both of them are correct. U2. U3 is that both of them are incorrect. And the worst possible outcome is when the expert is wrong and the other one is right. And then we denote it by default. So these are the 4 payoffs to the experts. And we can, to make it clearer, we can, without loss of generality, call the U2 and U3 plus minus 1 to scale it. And we denote by U1, we call it for simplicity alpha. So the only place where we're going to a little bit lose generality is with the U4. So in the symmetric case, anti-symmetric case, we assume that U4 is minus alpha, so the payoff of being correct alone is minus the payoff of being wrong alone. And we're going to just to, as a benchmark to analyze this situation. In the general settings, U1 and U4 can be different. And when they are different, we are going to look at one parameter that captures all the payoffs together. And this is the non-conformity gain ratio, which is basically the ratio between what I gain when I gamble correctly and go, and when I'm non-conforming, gamble correctly and be correct alone versus what I'm supposed to be incorrect together, versus the other way around, which is what I could have gotten if I was stayed with the other expert and was incorrect and was correct together, versus what I lost because I decided to be unique and then I was wrong. So this is the gain ratio, the parameter that captures all the payoffs together. And for the symmetric case, this is simply 1. Okay, so here are the payoffs, and here we see that the experts, of course, they want to be correct, but there are other considerations here, which are what the other guy said, and whether I'm going to mesh his signal or not. And just to give you a very intuitive result, if this gamma is very, 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 very large, say take gamma to infinity, it is always, regardless of information, regardless of signals, regardless of everything, it is always for my best interest to gamble. If I'm gambling correctly, I get a huge payoff. If I gamble incorrectly, the fine is not that bad. So don't play any strategic game. Couldn't care less about the signal. Just hear what the other guy says. Do the other way, and in expectation, I should get a high payoff. So this is kind of one way that payoffs here can drive the results.
But when you say the gamma can be different than one, this means that the assumption of what U4 is not.
Yes.
Okay. So this is just an example about U4.
So we have, I'll show the results to you separately. When gamma is 1, when U4 is minus alpha, this is the symmetric case. It is very nice in terms of benchmark. So I'll show first the results for this case, and then I'll skip to the general case where, by the way, where we see the humility threshold and the internet effect, we don't see in the symmetric case.
You don't see it.
So the symmetric case has nicer properties in terms of the way that some functions behave, but the interesting result happen when gamma is not 1. And so this is the experts. Also, we have a decision maker, and as I said, it's not very important, but he has some motivation in this game too. And what he wants to do, he wants to match the correct state of the world. So
he has a single strategy.
Yes, he has no strategy, but actually he doesn't have any strategies. But he does want the correctness of the process to be maximized. So he wants that, given the two experts, he wants the second opinion that he gets will be the correct one with the highest probability. So we're not considering the decision maker as a player, but as I said, in terms of mechanism design, for example, we are going to ask what can be done to maximize correctness, and which of the equilibria maximizes the correctness of the process and benefits the decision maker the most. So the decision maker wants the highest possible correctness, the highest possible probability of getting in the end of the process the correct recommendation. We also can compute this correctness to each of the experts separately, just to ask what it is basically the success rate. And it is interesting because these success rates are typically the parameters that are more known to the public and maybe to the decision maker and to everyone. So for example, if I look at a basketball player, I know his success rate. I know how the percentage of the shots he makes. I don't know his real quality or his real expertise level. I think that they are connected, but maybe a good player will be very well defended, and then his success rate will be lower than somebody else. Shots less. So
why it's not the same?
The success rate?
No, I mean the two equations. CI.
So
if you put I equals 2, it's the same.
Yeah.
And if I equals 1, it's Q1.
No.
No?
If I equals 1, it's the probability that A1 equals theta, which is Q1 if A1 is always S1.
That's okay.
But yeah, for the second expert, the correctness of the process and the correctness of himself is the same. The first expert has his own correctness, which depends on the strategy that he plays. Okay. And in terms of equilibrium, we identified 4 possible equilibria that, except for pathological cases, that catches all the possibilities in the game. So the first one, the first equilibria are the most straightforward. The first one is the herding equilibrium, which typically occurs, and this is only intuition, where expert 1 is much better than expert 2. And in this case, the first expert gives his opinion. The second expert simply repeats what the first one said, and he doesn't care about his own signal. basically have a herding of the second expert on the recommendation of the first. So when you switch them, we get the second equilibrium, which is the revealing one, where each expert reports his own signal. So the first expert says whatever he wants. The second expert, which typically in this case is better than expert one, doesn't care about what the first expert said and says his own signal, which should be with a much higher quality than the first one.
Just a question. So the decision maker should be going to be first and the second?
No.
What is the name of the question?
What are the strategies?
The decision maker has not.
The decision maker is not done.
Yes. The players are experts. They play some equilibrium in this game.
They decide who first or second time.
There's one that is first, one that is second.
Determined by the model.
Yes. I decide later as the designer of the mechanism, I said, well, in this case, maybe I should switch to improve society as a whole. But the decision maker doesn't get to choose who's first and who's second. He has no strategies whatsoever. And the experts also, they can decide who is first and who is second. They just, their approach.
So they find out the equilibria in which first case I decided that the more expert is the third. Then
yes. We have two experts named expert one and expert two. Expert one is the first, expert two is the second. Each one has his own Q. And in the herding equilibrium, expert one says his signal, and expert two says whatever expert one says. So
The equilibrium is Q strategy.
So here, so far, this slide is Q. On the next slide, we'll have a mixed equilibrium. So far, these two are pure. The third one is the guided equilibrium. In this equilibrium, the first one reports his own signal. And the second one also reports his own signal, unless when there's a conflict between between his signal, which is 1, and the signal 0, the report 0 of the first expert. So when he observes this kind of a conflict, he goes after A1. And then he also reports 0. So if he has this conflict, and we assume that 0 is the more probable state, then he goes with the more probable state and says 0.
When you say equilibrium, do you mean Nash equilibrium or some refinement of Nash equilibrium?
It's the base, it's the equilibrium given the.
So some reflection is not taken into consideration.
You don't. Yeah. You do have something.
don't understand why it's Bayesian and why it's equilibrium. We're talking only about the second expert place, because the first one always says his opinion, right?
In this slide.
Right, I'm talking about it.
So far, yeah.
The first expert always says,
Yes.
and the second one is not even a game. Maximizer is fail. Right?
So far, yes. But this is not always true.
The second third can choose to punish the first third if the first third deviates. If it's not a sub-inverted equilibrium, then you
But it's not repeated again. Why to punish it? You maximize the utility.
From not very
What Lauren is suggesting is non-subjective.
not
But
In principle, you're right, but the first one, there's no motivation, also plays like Max as a decision maker, because it's a strategia שולטת to disclose its signal. So there's not even a thing.
The other problem here is that you can't really punish because it's hard to find deviation. The deviation depends on your own signal. So, for example, if you want to punish the first expert for not reporting the signal, you don't know the signal, so you don't know when to punish.
I suspect it's wrong, so I must.
Very more like this. Then I say if you play 0, I play 0 as well. If you play 1, I play 0. Okay. Then I detect it from playing 1. Because then you get a low pair. But if you always play 0, you get a high pair.
Just to
Theory can move.
just to make it
There are second player in police playing also.
well,
Yeah,
it's
okay.
it's really hard to punish someone when you don't know the pairs,
Why?
but you don't know the state of the world. Maybe by punishing, you're actually giving him the good pair. So if you're playing 0 as the first expert, and I wanted you to play 1, me as punisher, if I play 0, 2, maybe we're both wrong and I'm not punishing
I
you.
suggest that under some values of Q, you can have an equilibrium. There 2, expert 2 always plays 0, and expert 1 also always plays 0. You ignore the issue.
And there are some values Q.
Yeah.
But then if you get Q equals 1. Sorry, if you get a signal of 1.
Yeah. Then you can,
No, it's not something else.
Yeah.
That's what he's saying. But your answer, David, was that you only consider sub-intelligence.
equilibrium.
So there may be other equilibria which are not sub-intelligent. That's what you're saying.
There might be. There might be, but we tried to look for some. We didn't go all the way, but we saw that it doesn't add up because of this kind of problems. You don't know the signal, and you don't know the state. So it's hard to construct an equilibrium where you actually punish someone, and where you find deviators and punish someone without knowing the state and the payoffs.
But you're not claiming that you know for sure that there are no.
I'm not claiming that there are no, let's call them crazy equilibrium or non-subgate perfect, but I'm claiming that these 3 and the next one are all the subgate perfect equilibria that they are. Okay, and the 4th equilibrium. Okay.
Which equilibria can you have simultaneously for the same set of parameters?
I will show it in 2 slides. Okay. So the last equilibrium that we have, and this is the one that in which the first decision maker doesn't always report his signal, is a mixed equilibrium. Here, the first expert, well, if he sees 0, tells 0, but if he sees 1, then he mixes. And maybe and sometimes says 0, sometimes says 1. The exact probability is, of course, designed to balance out all the pairs. And the second expert does the same. He also mixes. If basically he mixes between the guided and between reporting his own signal. So only when he sees his signal is 1 and the signal of the first expert or the report of the first expert is 0. He mixes between the 2 options, otherwise he just sets his own signal. And this is also possible for some set of parameters because we have this kind of best response dynamic, and the idea here is that, or part of the intuition here is that when we think about the guided equilibrium, the first expert can force the second expert to collude on his result. The first expert, if they play guided equilibrium, the first expert can say 0 and force the second expert to say 0, 2, and then, well, if they both wrong, then they both wrong, but the other one will not say 1. So the first expert has some power on the second expert, which the second expert might want to run away from by, let's say, doing something else. So this is kind of the problem that might be in this equilibrium that leads to the use of mixed strategies. And just to say another word about it, the mixed equilibrium is less important to us. It's interesting that it exists. It's interesting to show it, but it appears only in a rather small subset of the parameters. So in the rest of the talk, we will assume the parameters are such that this equilibrium does not appear. But this goes to your question. It is a game because for some parameters you can actually play mix, and you can force, and you need to consider the best response of the others. So it's not straightforward that the first one just says it's similar. Okay. So let's discuss the result and start with what Yigal asked about the parameters. So our first result is a mapping of expertise levels to equilibria. And this is under the symmetric assumption that U1 and U4 are -1 of each other. So gamma is 1, we assume P is fixed, we assume alpha is fixed, and we get a set of conditions that separate the expertise plane Q1, Q2 to 4 domains. And in each domain, the equilibrium that we play is unique, almost unique in the sense that this is what it asked. Only on the lines, the borders, you have the same equilibrium. So in the green area, you have a herding equilibrium, in blue the guided, and in the border between the two, you can have them both.
What is alpha?
Alpha is the payoff for you when you're the only expert that is correct.
And this picture is true for any fixed PNR?
Yes.
And it goes from P to 1?
Yes, it goes, this is the PB point, this is 1, this is 1. Of course, for different P's, it will shrink, and alpha doesn't play any role because it's hidden in the gamma equals 1 condition. So for every alpha, you get this. And this is basically also goes back to the intuition. You see that when the first expert is significantly better than the other, we have herding, where the second is significantly better than the first we have revealing, and when they're comparable, then they start listening to each other and have some kind of interaction, whether the guided or the mixed equilibrium. So this is our first result regarding the equilibrium, and I decided to show you all the results pictures rather than inequalities, because this is basically a set of inequalities that states what should be Q1 and Q2 to lead to each equilibrium. The second result is the computation of the correctness of the process. So what happens to the correctness? And here we assume that the mixed equilibrium in this graph does not exist. In the correctness, we can compute the correctness of the process for each type of equilibrium. And here we have a graph of the correctness when we hold Q1 fixed and we let Q2 change. So for low Q2, we have a herding equilibrium, and then the correctness is simply the expertise level of the first, because whatever he says is the second opinion as well. When Q2 is large, then basically the first one plays no role, and we listen only to the second one. So the expertise level goes up with Q2. And in between, in the area which is the guided equilibrium, when they actually have some kind of strategic interactions between the two, then we have correctness, which is higher both from Q1 and from Q2, because the second expert learns something from the first, he learns something from his signal, and then the overall recommendation is much better than whatever each of the experts could have done by himself.
In the Hellion equilibrium, it says that C is the maximum of Q1 and Q2.
Yes.
But here it's constant. So where's Q2?
Here,
Where's Q1?
this is Q1, and here's Q2.
So Q1 is 0.8 in this
drawing, yes.
everywhere
Yes.
0.8.
Basically, what we did here, we took this line, we go along this line like this. 2 exclude the mix. And what we get is that Q1 is fixed, and then as Q2 increases, we change equilibria and also the correctness changes. Okay, and the maximum is just a short way to say that in a herding, the equilibrium is the correctness is Q1, which is larger than Q2 because we're in herding. And in revealing, the correctness is Q2, which is larger than Q1 because we're in herding. Because we are revealing. So this is kind of a snapshot of our two main results or two objectives of the paper for gamma equals 1. And now we can go forward and discuss the asymmetric pairs and assume that gamma is not 1. So basically we can play with one of the parameters or the ratio between being correct alone and being incorrect alone. And just
did you think to compare these results with the model in which the experts can give some continuous advice, like between 0 and 1, because in this case, the second one, I mean, I think the graph would be much more smooth, right? But this is the next one.
In what sense they can give a...
Instead of saying binary advice, the expert says, most probably, or even the accurate number, my belief is that this is the probability, because it's a benchmark model for this idea of dividing it into binary advices. So we could see what should happen, I mean, in ideal world, and then what the restriction of a binary advice makes responsible for this interesting result. Because in reality, it's natural to believe that the advice is not continuous. So I think the model is good in this sense, but as a benchmark, I would think about the continuous model.
Strategically, it should be harder. They can give the number.
I don't. In which situation the second expert will not give the correct number, it's not clear to me. So you have to think about the utility, right? Because
maybe we need to redefine the utility.
Yes.
Now, I don't know.
Like the distance, the difference between the opinions or something like that.
I don't know. We need to think about it. Okay.
Distance.
It's a question because if you think about, I say that the state is 0 with probability 0.9. And so what is my payoff if I said that if the true state is 0 and what if the true state is 1?
Naturally the difference. Yes, likely. What is the utility now, the difference?
Possible. Okay, so let's go to the asymmetric case. So assume that Q1 is not minus Q4. And before we go to this case, we just introduce the logic notation just to make everything simpler. So instead of probabilities, we talk about ln of x divided by 1 minus x. And then our probabilities can be added in a nice way instead of multiplied. And the same we do with gamma. Instead of looking at gamma, we look at ln of gamma, and then everything is nice and additive. And this is just to make the presentation nicer. So when we assume that gamma is not 1, that gamma tilde is not 0, we can do the same analysis that we did in theorem 1. And when we assume that gamma is not very large, because as I said, when gamma is very, very large, then we have no strategic interaction. We just have the second expert saying the opposite of the first. So when gamma is not very large, and this is cutoff of being very large, the equilibrium can be determined by the value of gamma tilde. So for small gamma tilde, we have the herding equilibrium. for large but not too large gamma field that we have a revealing, and in between we have the guided equilibrium. And this is kind of because now we have a third parameter, so we can't really draw the same drawing as we had for theorem 1, but now we have this kind of way to decide, and this is what I told you, that if I am the mechanism designer, then I can choose gamma, but then basically, gamma here is liability of being wrong, or how the experts are punished for being wrong, or how they are rewarded for being right. But then I can decide by choosing the gamma that I want. I can decide which of the equilibrium they will take.
In the symmetric case, gamma theta is 1. It is just 1
Zero.
Gamma is 1 and gamma theta is
0, sorry, which is just 1 point. And that single point you have all the equilibrium. So here, if you fix 1 point, you have just one kind of equilibrium.
No, but you have all the equilibrium by playing with Q1 and Q2. So here you fix gamma, and by playing with Q1 and Q2, you get all the equilibrium by moving in this line. Here you fix the gamma, so here, but then by playing with Q1 and Q2, you move these lines, and then you can get the other equilibrium. It's already a
This usually is for a fixed one.
Yeah, it's for a fixed Q1, Q2, and P. You can change. I change gamma and you move between equilibrium. If you fix gamma, you can still play with it by changing the expertise levels of them. Do the same. Okay, so this is our version of theorem 1 for the non-symmetric case. And similarly, we have a version of proposition 1 for the non-symmetric case. Now, here, and this is what is interesting, is that when we look at the correctness level for the non-symmetric case, for some values of gamma, for example, here we show for gamma between P and Q1, the correctness function is no longer monotone and no longer continuous in Q2. So here is the same graph as the one I showed you. Q1 is fixed, Q2 is increasing, but this time gamma is no longer 1. And now we have this cutoff, which we call the humility threshold, where we move between the guided equilibrium to the revealing one. And as you see, in the guided equilibrium, the second expert considers both signals, or does some learning. And when we move to the revealing one, he no longer considers the first signal, and then his accuracy level drops. So we have basically, as an intuition, the correctness of the guided equilibrium is the correctness of the signal of the second expert, plus some benefit from the fact that he's listening to the first expert even when his signal tells him something wrong. It's the 0-1 case, and minus the correctness of listening to the first expert when the first expert is actually.
It's the opposite of humility.
What?
It's the opposite of humility. It's vanity.
Of course, it's the question of where you go, right to left or left to right. But we don't want.
Of course, that's the right direction.
We don't want him to cross this threshold. We want him to stay on the left side of the humility threshold, listen to other people too, and not only to himself. Okay. And of course,
there's no turning equilibrium because of where gamma and the
because of a crazy tuning of the graph that we did on this place. If you take that, if you can get the
okay, so it's not 0.
yes. You know, you have everything, you just want to focus on this. Yeah, and I think it's I do agree that the X's might be sometimes but in general it can always have all the equilibrium, of the equilibrium, just here we focus on this. And typically we have the same picture there too. If we change the order of the players. This is only for Q2, but we can also do the same idea of holding Q2 fixed and play with Q1, and you see that you don't want Q1 too bad, but this is not surprising. And the second result that I want to share with you is the intern effect, which discusses the order of the experts. So if we go back for a second for the gamma equal 1 case and this the drawing for the symmetric case, when we change the order of the experts, we simply move from one point to another to the symmetric point. So we basically either will stay in the guided area, or we jump from herding to revealing, and from revealing to herding.
Those symmetry between those two triangles?
Yes.
Okay.
So not really triangle, but there is symmetry between these areas. So typically when gamma is equal to 1 and you change the order of the experts, you stay with the same correctness, because as we said in the herding and revealing, you have the correctness is the maximal one, so it doesn't matter. And in the guided, the correctness is some formula which is showed before, it's actually the symmetric to Q1, Q2. So still you change the expert, but you don't get a better correctness. And this is not true in the general. So when we go to gamma not 1, for example, here we have a gamma larger than P, then we have a question of which of the experts we want to put in first. And as you see, we have some situations where when we change the order of the expert, we get a better result. And here, under this set of parameters, when we have the lower expert first, the lower quality expert, now we know them by QL and QH because it's no longer their position, but it's their quality. So the question is whether I want to go to L and then to H, or to H and then to L. So if I go to L and then to H, we get the revealing equilibrium regardless of the level. In this zoomed in graph, regardless of the level of the low level expert. And then I always get the same correctness level, which is the correctness of the high level expert.
You change here QL.
I change it here.
So what happens QH? The other one
is fixed.
But do the identities change?
The identities change between the green graph and the red and blue together. So in the green graph,
so in each individual graph, the identities do not change. So it's low and it stays low all the time.
That's the order.
yeah, identity in the sense of order.
Identity of who's the lower one and who's the higher one.
So I have a high level expert, which has always the same level, and it is always high. And I have a low level expert, which in this graph his level changes,
but stays
below. And then the question is whether I go to the high and to the low, or to the low and to the high.
Yeah.
And when I go first to the low and then to the high, I get this graph. So I always have a beginning equilibrium. The high level says second. It doesn't care about what the low level said, and we get always the same level of correctness. When we reverse the order, then first we have the high level expert, then we have the low level expert, and in some cases, in particular here, just before the humility threshold, the low level expert, it gives the best result because he's listening to the high level. He has his own information, which is relatively already a little bit better than what was there. And then this combined probability or combined posterior that he gives to the true state of the world is already higher than what the high level expert could have done by himself. So in this case, there is a point of changing the order of the experts.
We need not to be too sure of himself, because when he becomes too sure of himself, then
Yes.
he drops down.
And the red, how did you call the red?
The red is just
Did you switch the colors? Check this afterwards. If you switch the colors, it's gonna.
yes, yes, correct. So basically the blue is the guided, the red here is the revealing equilibrium, but this is the revealing equilibrium where the low expert doesn't listen to the high expert. And the green is also a revealing equilibrium, but it's a revealing equilibrium where the high expert doesn't listen to the low expert when they are reversed.
They are both revealing.
Yes. Because when you change the order of the experts, actually, by the way, to go back, this graph, these values have when smoothing through it, but there is no assumption here about the relative strength of Q1 and Q2. So basically, even when the second expert is better than the first expert, by choosing the correct gamma, you can make a low-level expert disregard of a high-level expert that speaks before him, and just say his own signal. So you can make, and vice versa, you can make a high-level expert be so afraid, this is maybe more intuitive, you can make a high-level expert so afraid of the punishment of being wrong together, of being wrong alone, that he will go for a herding equilibrium and say whatever the low expert says, just to make sure that the payoffs are plus minus one and not some very, very low minus U4.
You don't get guided in one of the orders.
Sorry?
One of the orders of the experts don't give it guided.
In
The last slide.
the last slide, not for this, not in this area.
Okay.
You can, again, you can get for any order of experts with the correct choice of gamma, you can get all the possible equilibrium. Here we just wanted to focus on this effect, so we just focus on the parameters where it shows and the graph is a little bit nice. But in general, yes, you have that when the revealing this one. Revealing is this one, and then if you lower the gamma, you can make them. If you change the order of the experts, and let the high level be second, then with a low enough gamma, you can always make it guided, and with even lower gamma, you can make the high expert disregard his own information, even very accurate, and go to herding a swoop.
Because when we break the RGB barrier, there are so many nice colors you can use. Aqua, lilac, what's that?
In the end, they will charge us for color graphs, so it will all.
We can all come down to our maybe attention how you done.
But no, I think up until this figure, we kind of managed to hold the colors together. Here is okay, so this is pretty much what I wanted to show you and discuss today. And the main takeaways here is that maybe non-intuitive, but can happen, that a better informed expert is not always good, neither in general. I don't always want to go to a second opinion, which is the best possible, because we saw the humanity threshold. And second, that maybe I don't want to go to the second opinion, the better expert in the second opinion, because he will disregard some of the information that he has. And the third point, which I said, and I want to emphasize that we can decide, if we know the expertise levels, we can decide which equilibrium they play. And so if we know how to limit the liability of the experts, or we can somehow play with bound the liability, we can ensure them or help them play the guided equilibrium, which is better for the decision maker. And what is interesting is that in here, for fixed Q1, Q2, and P, the range of gammas is relatively, I don't want to say relatively big, but there is some range of gammas. So it's not that I need to, for every two experts, I need to choose the correct gamma to force them to play a guided equilibrium. I can be very robust and choose some gamma in between, and then even if the experts are a little bit better or worse, then I'm probably still in this area, and then the result is a little bit to some extent robust, and so I can make them play the guided equilibrium, even if the experts have a different expertise level. But actually, if you can change the expertise level, only the difference here. Only the difference plays a role, and the weight is the plus minus P. And yes, so this is what I wanted to tell you today. If you have questions, I'm here. If you want to read the paper, I'm still here.